So now we're going to talk about Gauss's law. This is the first of 4 laws that eventually were summarized by Maxwell into the 4 laws of electricity and magnetism. But Gauss's law was first. Friedrich Gauss was a German mathematician. He actually did quite a bit in math, but he did some with electricity and magnetism also. And so this law is named in his honor. It's a different way to describe electric fields. So I'm going to write it. And then I'm going to explain each of the parts. But this left side is called the electric flux. We're eventually going to have a magnetic flux also. And you can see it's an integral. And also, the circle on here, that means it's a closed integral. You have to have a complete surface. So this doesn't actually work. Gauss's law does not apply just to a square, but it does apply to a cube. It doesn't apply to a circle, but it does apply to a sphere. So you have to have a 3D object. But first, let's go to a simpler version. Electric flux is also described with the letter capital Phi. So this is flux, and we put an E on it for electric. So if you have constant electric fields in area, this becomes just E dot A, or EA cosine theta. So electric field strength times the area that the field's going through, but there's a direction to the area. So this angle is between the electric field direction and the normal to the surface you're interested in. So this will make a lot more sense with an example. So I'm going to set up an electric field that is uniform. Uniform means the same. That's what we call them, school uniforms. Everybody's dressed the same. So this is a uniform electric field. And I really need you to think of it as 3-dimensional, not just drawn across the page. And then I'm going to take a square. And I am just going to start this with a simple square. We'll eventually build up to the cubes and spheres I talked about. But if I hold a square like this, so then you can shade it in if you want. Notice none of these field lines go through it. They go on top of it, they go underneath it, but if this is infinitely thin, none of the field lines actually pierce through the square. If I turn the loop, so this is a side view. So this is the same square, but turned, so it's edge on. Now, these 2 drawn field lines go through the square. So we have a lot of electric flux here, field lines going through the square. Here, there's no electric flux because the field lines don't go through the surface, they go on top and bottom of the surface. And then you can also have a circumstance where you tilt it. So if that's the same length, I think I did a pretty good job. Depending on where I draw it, of course, it's going to do 1 or 2 lines. But if we fill this in with, 30,000 lines, this isn't going to have as many lines going through it. So there's a lot of flux here. There's some flux here. There's no flux here. No field lines going through. All the field lines between the top and bottom go through. And the field lines that are that way go through. So to calculate this, we look at this angle. That's what really helps us here. So the normal to the surface, remember normal in physics and math, means perpendicular. So if this plane is like this, perpendicular to that is pointing out of the page. So the normal is outward. Well, then this angle between E and normal to the surface, E is this way, the normal to the surface is out of the page. I hope even with this, you can see that's a 90-degree angle. Theta equals 90 degrees. And so if I put this in here, the flux would be whatever the value of the electric field strength, whatever the value of the area of the square, times the cosine of 90 degrees. Well, cosine of 90 is 0. So there is 0 flux through here. Then in the side view, the normal again is perpendicular to the surface. So now I can actually draw it. This is the normal. And yes, we do use the letter N for normal. Well, this normal is in the same direction of the electric field. So theta is 0 degrees. And so we'd get EA cosine 0. Cosine of 0 is 1. So we get a lot of flux here. And then here, we would draw the normal like this. And we need the angle between the normal and the field. So we need this angle right here. So guesstimating, let's go with 60 degrees. I'm not sure exactly what I drew there. But then theta is 60 degrees because I drew it between the normal and the field. Like if I'd given you this angle, then that's not the angle you would use. Notice though, they are complements. So if this is 30 degrees, that's 60 degrees. So here, the electric field would be EA cosine 60 degrees. And I don't remember that off the top of my head. Shame on me, I should, because that's a special angle. So cosine of 60 is 0.5. So this would be 0.5 times EA. So if these are all the same square, we get the most flux if it's oriented so the lines pierce through the surface. We get some if it's tilted, and we get none if it's flat. I skipped telling you the unit of electric field. There's no special name for it. You know the electric field, it measures in newtons per coulomb. You know area is in meters squared. This can be ambiguous, so this is usually written as newtons times meters squared per coulombs. Okay? So now let's do a 3D object. We're going to do a cube, just to make things easy. So I'm going to redraw the electric field, and I'm going to do my best to draw a cube in it. So front face, side face tilted. This is actually one of the few things that I can do halfway decently. Drawing. I can do, I say that and then wow, have I done a not really good job. Imagine that's a cube. Okay. So there are 6 faces. So if I wanted you to tell me the total electric flux for this, you need to do the flux 3 times, once for each of the faces. But there's a lot of simplification. This top surface, the normal's upward. The bottom surface, the normal's downward. This front one, the normal, and again, you know, tilted the whole 3D drawing, but it's out of the page, and the back surface, it's into the page. So for all 4 of those, top, bottom, front, and back, theta equals 90 degrees. Another way of saying that is no electric field lines go through the top, or the front, or the bottom, or the back. So the flux equals 0. We only then have to worry about the left and the right. Now, for a 3D surface, the normal by definition is just always outward. So for the right face, the normal's this way. So the angle is 0 degrees. For this side, the normal outward. And notice that's opposite the direction of the field. So this is 180 degrees. So on the left side, our flux would be E, whatever the area of that face is, times the cosine of 180 degrees. Well, that's a negative 1. So this is minus EA. On the right side, we get EA cosine 0. Cosine 0 is 1, so this is EA. So if we add the 6 faces up, 0, 0, 0, 0, negative EA, positive EA, our net flux equals 0. Now this is because, I'm actually going to go back to Gauss's law now. Electric flux equals charge enclosed divided by epsilon naught. This electric field here is being made by some external thing. There are no charges inside the box. I know there are no charges in the box from these field lines because let's say there was a positive charge here, there would be more field lines coming outward. If there was a negative charge here, there would be more field lines coming inward. We couldn't have this nice, pretty uniform field. So since there's no charge inside this box, Gauss's law tells us the electric flux must be 0. So we can do curved shapes also. And so just to draw one. So that looks like a circle, but it's a sphere. Just go with it. This is a sphere. Well, even for the part I drew, we can't draw one normal direction. We have lots and lots and lots and lots and lots of normals. And what we would really do is we break these up into little patches of area. So this little patch of area would have a normal this direction. This little patch of area would have a normal this direction. This little patch of area would have a normal this direction. This little patch, this direction, and so on. Always outward. And that's when the flux equation turns into the integral. Okay? And you would add these all up. They are fairly complicated, so we're just going to leave them behind right now. So instead of this example, I am going to put a charge, a positive charge Q, and you know it makes an electric field outward. That's enough field lines. And now I'm going to draw a sphere. This is a sphere, and it is centered on Q. Pretend that that actually is true. So this is interesting. If we go to our flux equation, we have something slightly similar, easier. Every one of these points, now let me use black again. That little area has an outward dA. That little area has an outward dA. That little area has an outward dA. And so on, and so forth. Also, I know that the electric field is the same value everywhere here. Because if this sphere is centered on Q, you know E equals KQ over R squared. So if I'm always at the same distance from Q, I'm always at the same electric field strength. So in this integral, instead of E dot dA, I can do EA cosine theta, or EDA, sorry, cosine theta. Well, this is always, as I go around the circle, the electric field and the little normal to the tiny area are always in the same direction. So I can pull the electric field out of the integral because it's a constant. And this is cosine 0, so it's 1. So I just get integral dA. Well, the integral of a derivative is itself. So the flux through this sphere is the electric field times the area of the sphere. Notice I got a positive answer. We got a positive flux because all the field lines point outward. We also got a positive flux because the sphere encloses a positive charge. That's Gauss's law. The integral of E dot dA, which is the flux, equals Q enclosed divided by epsilon naught. We'll talk about epsilon naught eventually. Now I want to focus on the Q enclosed part. There's a charge inside this sphere. It's a positive charge, we got a positive flux. Only the charge enclosed matters. So I'm going to draw a different example with two charges. So I'm going to have a positive Q1, and I'll draw really long electric field lines. That's a good number. And we're going to have a second positive Q2, and I'm again draw lots of electric field lines. Oh, no, keep going, all the way across. So I want to do this to show why it's only the inside that matters. So I'm going to draw a sphere centered on Q1. Now notice there's both red and blue lines. All the red lines point outward, so I have lots of flux from the red lines. But notice what the blue lines do. The blue line from Q2, it comes in on this side and goes out on this side. So this little tiny piece of flux, when we add it all up, is going to have a negative value. And this, when it leaves, is going to have a positive value. They're going to cancel out. Here I didn't get them close enough together. Let me draw another one. But because electric field lines go on forever, all the field lines from Q2 that intersect this sphere go in and then go back out. They go in and they go back out. So there's no net flux from Q2. I get the same thing if I draw a separate sphere. So this is sphere number 1, this is sphere number 2, around Q2. Sure, I have a red line, but it goes in and it comes out. So it does not contribute to the flux. It cancels out. And then if I draw one, oh, let's do it here because there's such a crazy mess here. Number 3. Every blue one enters and leaves, enters and leaves, enters and leaves, enters and leaves. Every red one enters and leaves. Okay, there's only one red one. I can add more. Enters and leaves. So in number 1, the flux only depends on Q1. Number 2 only depends on Q2. And in number 3, flux is 0 because all these electric fields enter and leave, so there's no flux from them. Different way of saying it is there's no charge enclosed. So only the enclosed charge matters. So let's talk about that constant, and then we're going to make one more connection because we're going to go back to Coulomb's law. So I'm going to go back to, and I'm just going to write it, flux equals Q enclosed over epsilon naught. So epsilon naught has the value 8.85 times 10 to the negative 12 Coulomb squared divided by newtons times meters squared. Now you may or may not recognize that that unit is familiar. This is actually not a new constant. And I want to show you how. If we go back to the single charge, nope, 2 pages back, sorry. 3 pages back. Oh, no, it's right here. If we have a single charge enclosed, Q, in a sphere, we already figured out the flux is the electric field strength times the area. So let's do that. For a single positive Q, the flux we already figured out is E times A. And the charge of that was just Q over epsilon naught. We need, remember, this is important that that was a sphere, it was not a circle. The surface area of a sphere is 4 pi r squared. If you don't remember that, it is actually on the formula chart in the geometry section. So E times 4 pi r squared equals Q over epsilon naught. So E equals, and I'm just going to do them in a different order. I'm going to put all the constants in the front, 1 over 4 pi epsilon naught, Q over r squared. Well, but you already know the equation for the electric field of a point charge. It's KQ over r squared. So this has to be equal to this. So K, Coulomb's constant, is equal to 1 over 4 pi epsilon naught. And if you take 9 times 10 to the 9th and rearrange this to solve for epsilon naught with pi, you do get this value of epsilon naught. So when I forget epsilon naught, I use this fact, but it's on the formula chart, or it's on the constants chart. So the last thing then I want you to be aware of, you probably haven't looked at the College Board chart yet, but for Coulomb's constant, they don't write it as K Q1 Q2 over r squared. They write 1 over 4 pi epsilon naught Q1 Q2 over r squared. So we will do more with Gauss's law the next time. For right now, how to calculate surface area from E times A and that surface flux only depends on the charge inside. See you next time.